The quantum mechanical model of the atom, the particle nature of light. In this tutorial, we will be going over the particle nature of light, energy, Planck's constant, and frequency. Finally, some example problems involving energy, Planck's constant, and frequency. The particle nature of light. The photoelectric effect describes how electrons are emitted when light of a certain wavelength shines upon the surface of a metal. As a means to explain the photoelectric effect, Einstein proposed that light behaves not only like a wave, but also like a particle. Max Planck assumed that light energy can be either released or absorbed by atoms only in discrete packets of some minimum size. A packet of light energy is called a photon, or quantum, meaning fixed amount. The amount of energy, represented by E, in a quantum is directly related to the frequency of that quantum. To calculate the energy of a single quantum, we will use the formula E equals h nu, where E represents the energy of a single quantum, represented by the unit J. H represents Planck's constant, with a quantity of 6.626 times 10 to the negative 34, represented as the unit joules seconds. Nu, which is frequency of radiation, represented as per second, or cycles per second, or hertz. This relationship is included in the atomic structure section of the College Board AP Chemistry reference tables. Let's do some example problems. Calculate the energy of a photon with a frequency equal to 6.75 times 10 to the 12th per second. To do this problem, we will use the formula E is equal to h nu. So E is equal to Planck's constant, which is 6.626 times 10 to the negative 34 joules seconds, times our frequency of 6.75 times 10 to the 12th cycles per second. When we work this out to three significant figures, we find that energy is equal to 4.47 times 10 to the negative 21 joules, as seconds cancel seconds. Let's do another practice problem. Calculate the smallest increment of energy, a quantum, that can be emitted, which remember means released, or absorbed by a wavelength of 438 nanometers. So the first thing that I'm going to do is I'm going to convert my nanometers into meters, because I know that I need to find frequency, because ultimately I know I need to use the speed of light in order to find frequency. So I'm going to be starting out with the formula speed of light is equal to wavelength times frequency. And then, of course, I need to find frequency, so speed of light over wavelength. And before I go any farther, 438 nanometers line, and there is 1 times 10 to the 9th nanometers per every 1 meter. And then nanometers cancels nanometers, and 438 times 1 divided by 1 times 10 to the 9th equals 4.38 times 10 to the negative 7 meters. Going from there, I know that frequency is equal to speed of light, and speed of light is 2.998 times 10 to the 8th meters per second, divided by the wavelength, which is 4.38 times 10 to the negative 7 meters. And I've got this set up correctly because meters cancels meters, and I'm going to be left with cycles per second. So when I work this value out for my frequency, I get 6.84 times 10 to the 14th cycles per second. So now I have frequency, and because I have frequency, I can go over to my formula of energy is equal to Planck's constant times frequency, with Planck's constant being 6.626 times 10 to the negative 34 joules second, and then my frequency being 6.84 times 10 to the 14th cycles per second. And then the seconds cancel out and I'm left with my unit of joules, which is what I want at the end. And so when I work this out, it'll be 4.53 times 10 to the negative 19th joules of energy. And that is how I figured out how to calculate the smallest increment of energy that can be emitted or absorbed by a wavelength of 438 nanometers. Let's do another example. A certain type of radiation emits photons with an energy equaling 2.87 times 10 to the negative 18 joules. Determine the wavelength of a photon emitted by this radiation in meters. So in order to set this up, I have to work backwards compared to what I just previously did. So in this case, I'm starting with energy. So energy equals Planck's constant times frequency. I'm going to rearrange my formula to solve for frequency. So energy on top, Planck's constant, and then I'm going to plug my numbers in. So energy that was given to us is 2.87 times 10 to the negative 18 joules over Planck's constant, 6.626 times 10 to the negative 34 joules seconds. And when I work this all out for my frequency, I get 4.33 times 10 to the 15 cycles per second. So now I have frequency and I want to figure out my wavelength. So I'm going to go back to speed of light is equal to wavelength times frequency, rearrange my formula to solve for wavelength, speed of light, and frequency, and then I'm going to plug my values in. So wavelength is equal to 2.998 times 10 to the 8th meters per second divided by my frequency that I found from the beginning, which is 4.33 times 10 to the 15 cycles per second. And then seconds cancel out, which I am left with meters. So my answer in meters, notice here I don't need to switch over to nanometers, which I'm not too upset about. So 6.92 times 10 to the negative 8 meters. Let's do yet another problem. Calculate and compare the energy of a photon with a wavelength of 3.3 micrometers with that of a photon with a wavelength of 0.154 nanometers. Okay, so in order to set this up, we're going to call this wavelength 1, and we're going to call this one over here wavelength 2. So I'm going to do all the work for wavelength 1 first, and then do all the work for wavelength 2, and then we're going to compare the two. So let's start out with our information for wavelength 1. And so the first thing I'm going to do is I'm going to take wavelength 1, which is 3.3 micrometers, and I'm going to convert that into meters. So 1 meter, 1 times 10 to the 6th micrometers, and that is 3.30 times 10 to the negative 6 meters. And then I know that I need to figure out energy here. So I need to take that wavelength, and using the formula, speed of light is equal to frequency times wavelength. I'm going to rearrange this so it is frequency is equal to speed of light over wavelength. And my speed of light is equal to 2.998 times 10 to the 8th meters per second. And then my wavelength, which I just calculated, is 3.30 times 10 to the negative 6 meters. Meters will cancel out, and I am left with a frequency of 9.08 times 10 to the 13 cycles per second. So that is my frequency. So now that I have my frequency, I can find the energy associated with wavelength 1. So energy is equal to Planck's constant times frequency. Energy is equal to, so Planck's constant is 6.626 times 10 to the negative 34 joules seconds. Then my frequency is 9.08 times 10 to the 13th per second. So when I work this out, the energy associated with the first wavelength is 6.02 times 10 to the negative 20 joules. So that is the energy associated with the first wavelength. Now let's go ahead and do this process for the second wavelength. So now we're going to look at a wavelength of 0.154 nanometers. So I'm going to say 0.154 nanometers, multiplication sign in a line, 1 times 10 to the 9 nanometers in 1 meter. That is going to give me 1.54 times 10 to the negative 10 meters. Then I'm going to say speed of light is equal to wavelength times frequency. I need to solve for frequency like I did before. So speed of light over wavelength. Speed of light is 2.998 times 10 to the 8th meters per second. The frequency that I just calculated is 1.54 times 10 to the negative 10 meters. So my meters cancel here, so my value for the frequency here is going to be 1.95 times 10 to the 18th per second. Then, like I did in the previous example, I'm going to find the energy associated with the second wavelength. So energy is equal to Planck's constant times frequency. Planck's constant is 6.626 times 10 to the negative 34 joules seconds. And then my frequency is 1.95 times 10 to the 18 per second. Seconds cancel seconds, and I am going to be left with joules. So the energy associated with the second wavelength is 1.00 times 10 to the negative 15 joules. So when we analyze this, we could see the energy of the photon with the wavelength of 1, which is 3.3 micrometers, is less energetic. In other words, it has less energy than the photon with a wavelength 2 of 1.54, because the energy associated with that second wavelength is 1 times 10 to the negative 15 joules, compared to the energy associated with the first wavelength, which was only 6.02 times 10 to the negative 20 joules. So what did you learn? We went through the particle nature of light, talked a little bit about energy, Planck's constant, and frequency, and then did a few example problems involving energy, Planck's constant, and frequency. Need more help? Feel free to contact me. Have a great day.